So we'll finish up some of our examples from class. So let's get back to some friction and sliding or static friction. So let's take a look at this example one more time. We had a block that was moving up an incline, right? So we are told that it's moving, therefore it has a velocity up the incline. So then I know that the force of friction is going to be equal to the coefficient of kinetic friction multiplied by n. And so I'm guaranteed of that because of the fact that I am told that that thing is moving, and the force of friction is going to be counteracting that motion. So I end up with a force of friction that's acting down the incline, having a value of mu k times n. So that's how we ended up again with B is the answer. So as we take another look at our plot of the force of friction as a function of applied force. So what we have is a block sitting on a rough surface. What it has is an applied force to it, some force P. So all we're going to do is draw a free body diagram. What's that going to contain? It's going to contain the weight. It's going to contain the normal force of the ground, since the ground is now gone. There's our applied force P. And now we've got this force of friction. And so the force of friction maximum is the static force of friction, which is mu static times n. I know that the force of friction is going to be between 0 and force of friction max if we're in a static condition. If we know that it is sliding, then I know that the force of friction is going to equal mu k times n. Right? So let's work our way down to, look into this one more time. So the question that we're going to ask is, does it slip or does it stick? And that's what's going to affect the force of friction. So let's just kind of recreate an FBD KD here. So we've got an applied force P. We've got our force of friction. We've got the normal force. We've got the weight of the block. And then over here we've got mass times some acceleration. So let's go ahead and look at putting some values to this. So as it says right here, we're going to let the, say the weight is 0.2 newtons. And we have a coefficient of static friction and a coefficient of kinetic friction, 0.3 and 0.25. So what we'll end up doing is, if we analyze this and say it sticks, so therefore it's not slipping, that would tell us that the acceleration equals 0. And that would tell us, if we sum forces in the x direction, go ahead and put our coordinate system on there. If we sum forces in the x direction, that's going to tell us that P minus the force of friction equals 0, which is going to tell us that the force of friction is going to be equal to P. So we know that if there is no applied force, the force of friction is 0. And that would go all the way up to a maximum value, which would be equal to mu static times the normal force, which would be 0.3. And again, we would then solve for the normal force by summing forces in the y direction over on, again, in our FBD-KD system, that would tell us that the normal force is equal to the weight. So this is just going to be 0.3 times 0.2 newtons, which is going to be 0.606, newtons. So if the applied force is greater than 0.06, then I know that the force of friction is going to equal mu k times n. I am going to use mu k, and I'm going to have a known force of friction. For an applied force below 0.06, the friction force is going to be solved for, and again, we've already done that. We would know that the force of friction is equal to P, right? For P less than 0.06.